All right, so the last little run of the fall semester is always a bit chaotic because we have the conference with AICHE. Next week is Thanksgiving, and then the week after Thanksgiving, because it's so late this year, is actually the last week of the semester. So this is our last full week, I think, if I did my math right. And then we have 2 lectures next week, and then 2, and then that's it. Last day of classes, I believe that Wednesday. Maybe it's the Monday. I think it's the Wednesday. Because reading day, I think, is the 6th of December. So what that means is that basically, well, for content here, we're going to be sticking to StatMech. But today or tomorrow, the project will be posted. So that way it was gone over by Mahmoud and Abdur last week. So hopefully that was a beneficial exercise. So a little history behind that. That project is also for an NSF grant that I'm currently supporting some of my students under. Now for that grant, one of the objectives is for the NSF, you want to have teaching and research integration. So you are all the teaching integration to the research. But what that means is that what we'll be doing is we'll be compiling a database of VLE data that'll be used to calculate Kirkwood-Buff integrals. And that's going to be going into a database that we're going to manage. So that means that if somebody submits a project that doesn't follow the exact format of what we need for the database, that means it's going to be a heavy hit to your grade. So the formatting here is not just a formality, right? The formatting here is everything. So what we're basically doing is asking you, and just a recap of what everyone talked about last week, find some VLE data, make a hypothesis about how you think the molecules should be interacting on the molecular scale, give us the data, give us the Kirkwood-Buff calculations, give us the polynomial fits to the real data. Right? That's essentially what we're looking for, and then have the reference in a standard format so that anyone could go back and double check your work in the future. Does that make sense? So one reason why I like the Kirkwood-Buff integral and how it actually relates to this particular project is the objective of this project is to relate between molecular scale measurements and macroscopic measurements. So the Kirkwood-Buff integral connects those two together. So in essence, we'll be using neutron scattering, molecular simulation, and also macroscopic property measurements to make sure that they all three agree. And no one has really gone back and done this in a comprehensive way. So you are all participating in that endeavor. The meat of sort of how this fits into the overall NSF project will start to become more and more apparent as we move on in molecular simulations. And today, we're getting a little bit closer to that. So in terms of logistics, we're going to have the project and probably just one more homework assignment before the end of the semester because time is ticking down quite rapidly. I want everyone to have an opportunity to spend time on the project. Any questions about how that's going to be administered? Okay. So today, hopefully everyone remembers at least a little bit of StatMech. We can recap if there's any questions. But we'll be focusing on interacting molecules. And for specifically, we'll talk about monatomic gases. Because I think it highlights the principles of how we're going to handle this, going from a very, very low density fluid. In this case, today we'll be talking about kind of a medium density fluid. And then in the near future, we'll be talking about how do we estimate the properties of a dense fluid, which would be a liquid. So this would be a non-ideal gas, what we'll be talking about. So what we had determined before for an ideal monatomic gas, the energy of some state I is equal to, from the particle in a box, right? And this is the energy that is the kinetic energy of that single gas molecule. For a collection of molecules, we basically write that the total energy of some state I is going to be equal to the summation over all the particles slightly different form than we've written it before. We'll go over the details of learning it this way. So this is just the constants in front. But basically, the total energy of the system, we're saying, is just the energy of all of the individual states added up. So we have microstate I, and then we're using the subscript J to define our individual particles for this particular way of writing it. Now, in the case of interacting particles, this is no longer the only formulation we're going to consider. Right? The energy of the system not only depends on the energy of the individual molecules, but it's also going to depend on the configuration of the system. Right? If the energy only was dependent on the individual molecules, we would never have a liquid. Right? This is exactly why the ideal gas law cannot be used to predict the presence or existence of a liquid. So instead, what we need to add is we're going to define the potential energy of the system, U, is going to be a function of all of the positions of all of the particles in the system. And for now, we're just going to keep it as some arbitrary function. We're not going to give it an actual functional form. So the next step is that now the energy of some microstate I, right, which we would then put into, right, the probability of being in that state is e to the minus ei over kbt over the partition function, right, and vt. Just as a refresher from what we're doing. So now the energy of some microstate I is going to be the summation of the energy of all of the individual particles plus the potential energy. Right? I'm going to abbreviate it now, not just saying R1, R2, R3, R4, but I say Rn, meaning that it depends on all the particle positions. So this is where it's important that we kind of take things slow with the mathematics and think about what the implications of this is. What is the partition function? I'm asking for a volunteer to describe what is the partition function.
Isn't it like the total number of states that the system can take?
Effectively, yes. So for the canonical partition function, it's a little bit more tricky because you're scaling it by this Boltzmann factor here. Right? But let's say we're in the microcanonical partition function, right, which we could describe as omega NVE. Now, because of the equal a priori hypothesis, if all states have exactly the same energy, that means they're all equally probable. So the concept of the partition function, meaning the total number of states, is the most easiest to describe in the microcanonical ensemble. In the canonical ensemble, conceptually, it still takes the same idea. Right? So we still need to consider all of the different ways that we can describe the energy of the system. Now the difference though is that we factor that here, meaning that the higher energy states are less probable, and that's where we get the microcanonical ensemble. Okay, so this has very, very serious implications for how we handle the potential energy function for a collection of particles. What that means is that every single possible state of the system is saying that not only do we have to consider all of the different possible kinetic energy distributions of the gas, But now we have to consider every single possible orientation of the system as well. Now that means holding all the particles in a fixed position and moving around particle 1. Then holding all the particles in a fixed position and then moving particle 2. And then holding all the particles in a fixed position and moving particle 3 around. And you have to repeat that process for every possible configuration of every possible particle. Right? So for one snapshot, you move all of molecule 1, all of molecule 2, all of molecule 3, all of molecule 4, all the way up to n. Then you rearrange to have another snapshot, and then repeat that for all of particle 1, all of particle 2, all of particle 3. So what that ends up meaning is that our partition function, if we substitute this all together, we are going to have the indistinguishability factor, just as a reminder, right? The partition function for a collection of particles is going to be given by here. We're going to have our indistinguishability factor. We're going to have our contribution from the kinetic energy. 2 pi T over H squared. We also have, okay, so just to label this, this is our indistinguishability factor. This is our ideal monatomic gas. And then now we're going to have a contribution here from our intermolecular potential, or sorry, our potential energy. And it's going to be a bit of a doozy. So we're going to have some constant, and I'll show you why we have this here. But we're going to be integrating over the volume for all of the particles, basically removing every particle to every position in space. That's why we're integrating over the volume here. I'll give you a second on this one, because it's a doozy. So in this formulation here, we have a series of n nested integrals for each of the n particles in the system. And what this integral here is basically saying is conceptually what I mentioned before. You have to consider every possible configuration of every possible particle. So in practice, if we think about this in a, let's just keep it as 3-particle system here. Particle 1, particle 2, particle 3. For example, let's just say now they're distinguishable so we can consider this here. What that basically means is that I'm going to lock in position of particles 2 and 3 and then move 1 to every other point in space. Then I'm going to move 2 and 3 to different positions and then integrate again all over 1. Then I'm going to move 2 and 3 to different positions and then move 1 all across the board. Then once I've done it for all the different positions, then I repeat that for 2, then I repeat that for 3. Suffice to say, we don't have an analytical solution for this. Right? But conceptually, it makes sense that that captures the spirit of the partition function. Right? That is our ultimate objective. So basically, all the formulations that we have for equations of state with statistical mechanics come about in approximating what we call the configuration integral. So now, in the circumstance if, in the circumstance, the limiting case where we have no interactions between the molecules, that means e to the 0 is just equal to 1. This whole term right here goes to 1. So we're just integrating over the volume for n number of particles. So in this formulation, what we say then is that this constant will be v to the minus n, such that this constant here cancels out with the volume term in the partition function that we did originally. Because if we evaluate this integral, now we're going to call this z, the configuration integral. So then if u equals 0, we reestablish our non-interacting properties. Next, we know that the pressure is related to the Helmholtz energy, right? The canonical ensemble is NVT, which means it should be most closely related to the Helmholtz energy. Now in this circumstance here then, the pressure, since Helmholtz is equal to minus kBT ln of Q, that means the pressure and in the case of if u is equal to 0, we should get out the ideal gas law. So what we've done is we've lumped basically all of the non-ideality into this configuration integral. So what our objective is going to do is I won't go through the math to a large extent, but basically the objective that we're going to be doing now is more or less trying to approximate this integral to get some useful information based on how do molecules interact, right? This is what we're trying to get at. So now we're simplifying the system down, right? So when we went from a monatomic gas, we were only considering the kinetic energy. When we went to a diatomic gas, we were considering rotations and vibrations as well. From a polyatomic gas, you have additional forms of vibrations and rotations and torsions. These are all different ways that the system can store energy. Now the next complication is what happens when the molecules are interacting. So the key thing, what we're doing here, is we're not basically saying, oh, I don't know how ethylene behaves versus ethane. I'm going to go into the lab, I'm going to measure PV isotherms, I'm going to measure heat capacities. Right? That's the classical approach. The classical approach is we don't know what's making up this fluid. So I'm just going to go into the lab and measure it because we need it. Right? So in a classical thermal approach, that's the only thing we know. We didn't know that molecules existed. We didn't know the property differences between them. In statistical mechanics, we're trying to be able to predict those properties now. So in the case of a particle in a box, we're saying, let's assume that particles behave like billiard balls and that they only store energy in the form of kinetic energy. We developed a model for that. Now let's say for a diatomic gas, we're saying, okay, we're going to use a rigid rotor molecule for the rotations. We're going to use a harmonic oscillator model for the vibrations. Now we've simplified it again even still, saying, okay, let's say, for example, we have interacting molecules. How do we model what the attractive and repulsive potential energy is for a collection of particles? This is sort of getting at to the core heart of the physics of how the system is actually behaving. So now what we need to do is simplify that configuration integral so that we can have that discussion about how different particles should be interacting. So, let's say we have a system of only 3 particles. 2, we're going to say that we're going to approximate this potential energy function that has some arbitrary form as the contribution of interactions between particles 1 and 2 plus the interactions between 1 and 3 and 2 and 3, and then lastly there'll be a correction term. I'll call it U prime, R1, 2, R3. So these are going to be called binary interactions. And just for thoroughness, actually I'll do this one here. This is just the distance between those two vectors. So if we write this out graphically, just so it's clear, let's say we have particle 1 and particle 2. In our notation, the R vector, all that's saying is what's the position of the molecule. So in this case here, this would be R1. Would be R2, and 1 minus 2 would be the magnitude of that difference. So what we're saying here is that if we have a collection of particles, particle 1, 2, particle 3. In this approximation, we're going to say that this term is 0. This is the pairwise additivity assumption. Basically, every type of calculation or simulation that is done uses this assumption here. So in many ways, it's sort of a core tenet of statistical mechanics. There are some exceptions where people use multi-body interactions, but it's really sort of a post hoc rationalization necessarily. This is the backbone of all of what we do. So just like in classical thermodynamics, we sort of did a nice, beautiful, elegant formulation. And then eventually we got to the point where the functions they were trying to approximate were too complicated. We've reached that already in StatMech. So what this is saying is that the total energy of this system in terms of its potential energy is going to be the contribution of all of these pairwise functions. So the energy is energy 1, 2, energy 2, 3, plus energy 1, 3. Okay. So what this means is that we are now going to approximate this very complicated, arbitrarily difficult contribution from the potential energy of the system based on positions. as the summation of the pairs of interactions. So this little notation right here is basically preventing us from double counting. So we're saying that we're going to start from I is equal to 1, but j has to be greater than or equal to, or actually it has to be greater than I. So if we apply this notation here, we'll start off with I is equal to 1, which means that j has to equal 2, and then j has to equal 3. That's n. Then we repeat, I is equal to 2, which means j has to be equal to 3. This avoids us from double counting, this notation here. So now if we substitute this expression into our configuration integral, we have some big, again, complex, scary function. So now what we need in our model is some function that describes how two atoms are going to be interacting. So this term right here, r, the magnitude of rj, so basically we're going to say it only depends on the separation distance between the molecules. This is called a pair potential. And what it represents is the potential energy it's the potential energy between two particles as a function of their distance from one another. So let's consider some limits. As r, let's just say, instead of using the notation, let's just call it r now. As r goes to infinity, what should the pair potential go to? 0. And what limiting case is this? This is the ideal gas scenario. As the molecules are infinitely far apart, or far enough that this function goes to 0, we should have this function reduced to 0, which means that if we integrate this expression, e to the 0 is 1. We integrate this, we just get v to the n, which is what we get out for the ideal gas case. Now, as r goes to 0, our potential should go to what? Not negative infinity, but positive infinity. Negative infinity means that it's an infinite sink, that the molecules will want to all fall on top of each other. When u goes to infinity, that means it takes an infinite amount of energy to get two particles to overlap, which is the real physics of the situation. Right? We cannot have the electron clouds overlapping, otherwise two electrons are occupying the same orbital in the same state. So this brings us to models, simple models of fluids. So those of you who have an interest in physics, you will see these terms pop up quite substantially. Has anyone heard of the hard sphere model? Few folks. By show of hands, who's heard of the hard sphere model or a hard sphere fluid? Okay. So what that means, that's the first and simplest one. So a hard sphere potential, you can draw it out, the potential energy as a function, I'm just going to use r instead of rij just for simplicity's sake. All that it means is that the potential energy is equal to, for R less than sigma, it is equal to infinity, and for R greater than some value, it is 0. I think I wrote this weird. This is not how you write a piecewise function. It is equal to infinity for R, let's say less than or equal to there, and 0 for R greater than sigma. So basically it's saying that there is no interaction between the molecules until they come in contact. If they attempt to overlap, the potential energy goes to infinity, and of course, due to energy conservation, you can never have an infinite amount of energy, so that state is never possible. So the probability that the system is overlapping, probability is equal to e to the negative I over kbt over the partition function. As the energy goes to infinity, the probability goes to 0. So this is no-no. So the only thing that happens in a hard sphere fluid is that the particles just physically can't interact. Now the next simplest potential, so these ones here, these are actually, there's been a resurgence of people investigating hard sphere fluids, because in the hard sphere model, the canonical partition function is equal to the microcanonical partition function, which means that all states are equally probable. And the additional interesting thing about this as well is that in a hard sphere fluid, there is no potential energy in the system, right? Because it's either 0, which means there's no potential energy, or it's infinity, meaning that state can't exist. So the only states that can exist are ones with no potential energy of the system. Now the consequence of that if there's no potential energy in the system, that means that the free energy is 100% controlled by the entropy of the system. So hard sphere and hard particle models are really interesting from a physics perspective because it explains what happens in the limit of entropy-controlled systems. Right, which I find interesting and motivates a lot of the research that we do in our group. But that's why they're of interest from a fundamental perspective. These fluids don't exist, by the way, right? This is all a fanciful model, but in the limit of this case here, it does tell us what is the potential contribution from strictly excluded volume effects. If you consider that the model of the molecule cannot overlap, how much of the fluid properties comes from the fact the molecules can't overlap? And it's actually a surprisingly large amount. Now the next simplest one. Now in the hard sphere case, you can never have a dense liquid to a low density liquid phase transition. In a hard sphere potential, you can have a solid dense fluid transition. That one's not too bad because it's really more like imagining that you're packing enough spheres into a space until they start to jam. So you can crystallize spheres by packing them closer and closer and closer together. So you can have a solid liquid transition in a hard sphere particle fluid as a function of the density of particles, but you can never have a high density, low density phase transition because the liquid is disordered, the gas is disordered, and you can never force order because there's no potential energy. Now the simplest fluid where we can model phase transitions, and again, this is another physics type approach where we're using the models to understand what are the limits of certain behavior, and that's going to be the square well potential. Now the square well potential is the simplest potential where we can get a fluid-fluid phase transition. It looks similar to the hard sphere potential, except it's a little bit different because it includes a potential energy sink. Okay, so again, we have some value of sigma that represents the size of the molecule. In this case now, we have a depth of a well. So we have some little bucket that at a certain separation distance, the molecules will fall into a potential energy well. That state will be at a state of lower potential energy, which means that it'll be at a higher probability. So if you're trying to model a dense fluid, you can approximate how far apart the molecules are based on measurements using diffraction, which we'll talk about in a little bit towards the end of class. Towards the end of the course, I'm sorry. We can use this information to tune models to basically say, we know that, let's say, argon fluid at 70 Kelvin has an average molecule separation distance of, let's say, 3.2 angstroms. Then you would know that when you're modeling the potential energy interactions, there is a certain separation distance away. So if we were to write this one in terms of its pairwise function, this would be equal to infinity for r less than or equal to the sigma. It would be equal to negative epsilon between sigma r and r squared. Well, sigma, this is just some parameter, just scaling how big this box is. And then beyond that, it would be 0 for r greater than r squared, well, sigma. These are just parameters. So now, if we can consider the free energy of the system, either Helmholtz or the Gibbs, if we have potential energy, now we have an interplay between energy and entropy, and we can accomplish that phase transition between two fluids. So this is the simplest potential where we can do that. So these are fun potentials to more or less play around with the limits of what physics will tell us can happen for a molecular system. Now the last one that we'll talk about is going to be the one that most simulations will actually use in terms of trying to model how molecules behave. So I don't have the exact statistics, but I would say probably greater than 90% of every molecular simulation paper that's published uses this potential. And this is the 612 Lennard-Jones potential. Okay. All right. So the 612 Lennard-Jones potential is the most commonly used intermolecular potential in real fluid simulations. So if you were to go basically in whatever discipline that you're in and just search for a molecular simulation paper for some fluid of interest, chances are they used this model to model the potential energy of interactions between the particles in the system. So let's break it down a little bit. This part right here, this is attraction. This part here is repulsion. The sigma and the epsilon represent basically the size of the attraction, and the epsilon corresponds to the strength of the attraction. Now where it comes from is that this region here is 1 over r to the 6th. This is from van der Waals London dispersion forces attraction. And this is actually a fairly sound theoretical foundation for that particular functional form. So what the Lennard-Jones potential says is that, okay, we have attraction that depends on the radius, sorry, the separation distance between the particle to this 1 over the 6th power. So it's a very short range attraction. Now that would lead us to having all the molecules stacking on top of one another. So instead, they also have a 1 over r to the 12th attraction added into it. The resulting function is this curved feature that's characteristic of a Lennard-Jones type potential. Now the 12 is a little bit less found in science. Now the objective oftentimes of molecular simulations is to improve how many particles you can include in the simulation, increase the duration of the simulation, and that's all based on the computer power. So if you can reduce the number of computational steps in order to calculate, let's say, the potential energy function for your collection of particles, right? Let's say we have 10 particles in the system. That means I have to calculate this function here between particles 1 to 2, 2 to 3, 1 to 4, 1 to 5, 1 to 6, 1 to 7, 1 to 8, 1 to 9, 1 to 10. Repeat that for 2, repeat that for 3, repeat that for 4, repeat that for 5, 6, 7, 8, 9, 10. And that's for 10 particles. We're talking about millions of particles in a system. And you do that every, let's say, couple of femtoseconds to calculate the properties of a molecule over the course of nanoseconds. That's a whole lot of computational cycles in the simulation. So the repulsion term is just the attraction term squared. So that if we can come up with sort of computational methods that allow us to calculate squares of functions quite rapidly, then that allows us to say, okay, we'll get the attraction part right, and then we'll do an empirical relationship for the repulsion because it's computationally efficient. Now those limitations are becoming less and less severe as computers become faster and faster, but this is still more or less the lion's share of what is going on in an actual simulation. So it's a little anticlimactic in terms of that sense. So just as a recap, and on Wednesday we will relate this back to the configuration integral, but I just wanted to re-remind everyone sort of the objective of why we're doing all of this. Now, who feels comfortable with the concept of a radial distribution function from last week? Abdur discussed it, right? I'm not having a fantasy here. So, I was in Orlando as well. So the radial distribution function is some function that we can calculate based on the atomic positions of a real fluid system. It's the way that people who practice statistical mechanics and simulations and molecular structure, that's how they communicate to one another. The radial distribution function contains all the information to know what is the organization of matter, basically on an averaged basis, because we don't really care what a snapshot is. We want to know what the ensemble average is. The radial distribution function is the way that we communicate. So if nothing else, of all of this StatMech discussion, if you can read and understand what a radial distribution function is, how it's generated, I will consider this a success. Because if you go to a job interview for any company that deals with molecules, which I'm assuming most of us will be in that situation, if you do not know what a radial distribution function is, you will not be able to communicate with a chunk of the people at that organization who do that type of research. It's a very important physical concept to know. So, if we have the positions of all the particles in the system, we can calculate something called the radial distribution function. There's lots of different notation. Oftentimes I see it as rho of r. This is some function that describes the average order in the system. So it'll look something like like this right here, okay? Now the key question is, how do we use this information to give us access to the average ensemble of the positions in the system? And from that, the simplest one is through molecular dynamics. Now we'll do a more in-depth discussion of molecular simulations, but I just wanted to, because we're talking about this here, I don't quite have enough time to go over relating it back to the configuration integral. But in a molecular dynamics simulation, what we're doing is we're basically going to take a collection of particles and we're going to kick them off in a random velocity. Now the velocity here is going to be such that it follows the Boltzmann distribution. Now what we're going to do in a molecular dynamics simulation is that if these particles are completely non-interacting, they're going to hit the wall, they're going to bounce off. They're going to hit the wall and bounce off. They hit each other, they're going to bounce off elastically. So if they're hard particles, they're effectively going to hit each other and then bounce off elastically. But that's not necessarily how real fluids are going to behave. So in reality, this molecule here is going to be pulled a little bit by this one. So if I call this 1 and 2 and 3, there's going to be some potential energy between 1 and 2 that's going to deflect its movement. Right? So going back to the example that we talked about with water, if we were water molecules and we were liquid water, there would be like, what, 200, 300 of us in the room? There is certainly going to be a contribution from attraction and repulsion, or basically, in our case, I would say that if we are having 300 people in the room, we would, I mean, theory would say that we're in our equilibrium position, but I think we would probably be in this region over here, being unhappy, being that close to one another. So the objective of a molecular dynamics simulation is to basically treat all of these particles as more or less kind of like a magnet, right? Whether or not you're attracted or repulsed, and that will modify the trajectory of the particles a little bit, and it'll give you a more accurate representation of the real fluid structure itself and the real fluid properties. So why this all matters, now we can take this information and we can put it into the configuration integral and we'll derive the virial equation of state, and that's what we'll do on Wednesday. But the virial equation of state has some severe limitations at high density fluids. Any high density fluid simulation is basically going to be what you need to do to calculate properties. There are some equations of state that are based on statistical mechanics for high density fluids, but they rely on a tremendous number of tunable parameters. It's not simple like the Peng-Robinson equation that all you need to know is the eccentric factor at its critical point. Right? So if you want to optimize an equation of state using stat-mech principles, you need to have maybe 3 to 4 tunable parameters for every single molecule, not just the critical point. So it gets a little more complicated. So simulations is going to be the major application of all of this contribution here. All right. Any questions? All right. See you on Wednesday.